Question 19. A ball of mass 0.15 kilograms is thrown vertically downwards from the top of a building to a concrete floor below. The ball bounces off the floor. The velocity versus time graph below shows the motion of the ball. Ignore the effects of air friction. Take downward motion as positive. For this example, they did not have to tell you that downward motion is positive. We have a velocity time graph. Always look at your vertical axis to see what type of graph they have given you. It's a velocity time graph, and the gradient of a velocity time graph gives you acceleration. In this case, it gives us gravitational acceleration because this is a vertical projectile motion example. A positive gradient means that g, the value of g, is positive 9,8 meters per second squared. So down is positive. So all these velocities above the timeline are down, and all the velocities below the timeline are up. So I've indicated it like that, which is a handy hint. If as soon as you've established whether down or up is positive, do those brackets on your graph, which makes life much easier. So let's look at what happens on this graph before we even start answering the questions. The ball is thrown downwards, so it leaves the thrower's hand at 10 meters per second. It's going to hit the ground at 20 meters per second. What happens then? It bounces up. Up is negative. All of these velocities are negative. So it bounces up, reaches the highest point, and then comes down again. I've done a little sketch like this, and I do advise you all to do that. This motion is down, this motion is up, there it is, and that motion is down again. I've used colors which may be hard for you to see on the screen. So we're going to read through the questions. At this stage, I would advise you to read through all the information above the question, above the graph again, but we're not going to do that because of time. 19.1, from the graph, write down the magnitude of the velocity at which the ball bounces off the floor. With what velocity does the ball leave the floor? Let's look at the graph once more. It leaves the thrower's hand, hits the floor, bounces off the floor. So with what velocity does it leave the floor? It leaves the floor at 15 meters per second upward. They asked you for the magnitude of the velocity, so you did not have to give the direction. I put it in there just so that we could establish the directions here. Then in 19.2, is the collision of the ball with the floor elastic or inelastic? Refer to the data on the graph to explain the answer. It's an inelastic collision because the ball hits the floor at 20 meters per second and bounces back up again at 15 meters per second. So kinetic energy is lost in this collision with the floor. 19.3, calculate the height from which the ball is thrown. We want this value. How high above the ground was the ball thrown? Now we could sometimes solve questions like this using the area under the graph, but in this case we cannot because we do not have the time, and this also looks like a little bit of a skew line, so we don't know what the time is after which it hits the floor. So we're going to use equations of motion. There are many different options. We're going to use this one. It's the quickest one, where the final velocity with which it hits the floor is 20 meters per second. Initial velocity with which it leaves the thrower's hand is 10 meters per second. We want the height, delta y. We've got a or g, so the height is 15,31. They only want the magnitude here because they state height, but if they wanted displacement, the sign is correct. It's positive 15,31 because down is positive. You could have done this alternative method where you use that equation to find the time during which it falls. Once you have the time, substitute into this equation, you will get exactly the same answer. There are other equations that are available to be used for this as well, but I'm not going to go into all of those. In 19.3.2, calculate the magnitude of the impulse imparted by the floor on the ball. So the floor is exerting a force on the ball in order to make it bounce upwards. Whenever they ask for impulse, you can calculate change in momentum. We have the mass of the ball. The final velocity for the bounce is 15 upward, negative 15. The initial velocity for the bounce is 20. It hits the floor at 20, rebounds at 15. So when you substitute your values in, you get a negative answer, but they asked you for the magnitude of the impulse. So we're going to write it as positive 5,25 Newton seconds. Please remember it's not newtons per second, it's newtons seconds, or you can use the unit kilogram meters per second. The negative sign is correct because the force on the ball is upwards. 19.3.3, calculate the magnitude of the displacement of the ball from the moment it is thrown until time t. The ball is thrown and then it rebounds up. So they want it from that moment to that moment, they want the displacement. We already worked this out in 19.3.1, the value was 15,31. So if we can work this out, add the two together, we'll get the displacement from there to there. So we're going to use, for the green part, we're going to use this equation, Vf squared equals to Vi squared plus 2a delta y. For the bouncing up, final velocity is 0. Initial velocity is negative 15. Substitute your values in. You get an answer of negative 11,48. We have a negative sign because this motion is upwards. Remember, upwards is negative. Now we're going to add these two values, and that will give us the displacement from the moment the ball is thrown until time t. So my previous answer, I've got it all in red, so I'm going to continue with that. So the total displacement is the downward motion, 15,31. Add your negative value, your answer is 3,83 meters. Then in 19.4, sketch a position versus time graph for the motion of the ball from the moment it is thrown until it reaches the maximum height after the bounce. Use the floor as the 0 position. Indicate the following on the graph: the height from which the ball is thrown, which was 15,31, and time t. So they want a position time graph just for this section, the downward throw and the upward bounce. Now the floor is your reference point, so the ball cannot go past the floor, so your graph will all be on the one side of the timeline. Up is negative, down is positive. So when it comes down, my graph must be one of these two graphs, and when it goes up, which is the negative direction, it must be one of these two graphs. Your position time graphs will always be curves for projectile motion because it's accelerating. The object is accelerating. So positive direction, which in our case is down, will be one of these two, and negative directions, which is up, will be one of those. So our ball is going down in a positive direction. So we start here, we go towards the floor. It's going faster and faster, so the gradient is becoming steeper and steeper. It starts, we write it as negative 15, goes towards the floor or the ground. The ground is your reference point. Positive direction towards the floor. And then it bounces away from the floor, which is upwards, and up is negative. So it must come away. So it leaves the floor at 15 and it goes slower and slower, so until it reaches the highest point at time t. So it's a steep gradient becoming flatter. This is a flat gradient becoming steeper. This is going faster and faster, and this is going slower and slower. Positive direction, negative direction. These graphs are all you need to remember in order to draw the position time graphs. It's difficult to draw a position time graph when you have taken down as positive and up as negative. But in this case, we had to do it this way around.